Okay, good. Okay, now let me present my screen. Yeah. So now let us just have a look. Just have a very quick go through this image. Okay, I'll show you this image on the PPT also, or either you take a photograph of it or screenshot of this and just go through with this image a little bit. Then I'll tell you what is the difference and how we proceed in a particular sensor. Okay, so you have a current loop for which your voltage output is provided. Okay, okay, through a transmitter which takes a physical phenomena, transform it into a suitable voltage supply to your current loop. Okay, which is received by a receiver where it can process it, display it, or can control a particular process with this. Okay, this is your current loop. You have a power supply, or you can say a power source. It can draw infinite current, but that infinite current has to be constrained in 4 to 20 milliamp by a resistor. Okay, and the resistor of receiver, and from here you get an voltage output with a particular resistance. Okay, some resistance and some voltage. Okay, you can say a combination of a voltage and resistance. Okay, so just have a quick view of this and then we'll go proceed. Okay, so let me start. Yeah. Okay, so 17 of you have attended. There are 4 students who are missing. There were 20 students that those were in the session. Where are these 3? Where is Ritik? I think Ritik has some internet issues. But what about the other 3 students? No idea. So okay, let us just continue with this. So now you have a transmitter. Okay, suppose this is your transmitter. Okay, suppose this is your transmitter. Let me use a pen. Like, okay, okay, and this is your current loop. This is your current loop. This is your voltage. Okay, now there will be an resistance. This is a resistance. There will be a resistance so that this voltage is not driving an infinite current. Okay, so in order to range it, we can add a resistance to it also. Okay, then you will have a resistance for your receiver. Okay, from which you can get the output of your current. Okay, output of your current. Okay, and you can get the display, or you can get control through this value. Okay, your loop is going to work like this, and this is your transmitter. So first of all, let us consider the case of your thermocouple. Okay, so you know that your thermocouple is going to provide a voltage to your transmitter. Okay, there will be a certain kind of voltage. Okay, now when there will be a certain kind of voltage, that same kind of voltage cannot be fed to this circuit. It has to have some different characteristic, and that characteristic will be changed by the transmitter, and it can be a transmitter can be worked like an, you can say, amplifier. Okay, or it amplifies this particular circuit and provides it to the current loop. Okay, so there will be an voltage, and now you can see that the voltage is of different polarity. Okay, this current is always of different polarity, so that we can alter these situations and have a voltage drop. Okay, so we always use the reverse polarity for a transmitter. Okay, so in this particular case, it is acting as an, what you can say, although it is a combination of, you can say, voltage and a resistance. Okay, this resistance is because of the induction of a new system into the loop. This resistance is because of the induction of a resistance of a new system into the loop, but primarily what it is doing is it is providing you an resistance. And when it is going to be like this, when this is your thermocouple, when this is your thermocouple, and let me add, yeah, when this is your thermocouple, this is your thermocouple. Let me just repeat it again so that you have a very good understanding of what is happening. Step by step, if there would have been only a voltage for a particular circuit, there would have been infinite current in this particular circuit. Okay, there would have been infinite voltage in this particular circuit. Now, class, can you just give me a minute? Just a minute. I have some very urgent call to attend. Just a minute. Okay, class, just a minute. I will do that. Yeah, 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 yeah. So after this session, I will take the meeting. Okay, I'll call all the experts and just take a single meeting. Yeah, yeah. Okay, sir. Okay, 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 sir. Students, there was a urgent call. Sorry for the interruption. So shall we continue, class? Kindly say yes or no. Shall we continue? Yeah, yeah. Okay, good, good. So let me take it one by one. Okay, just one by one, very with a very simple language. Okay. So that you just have a very good understanding of it. You will have a current, and that current will be infinite if there is no resistance. To make it finite, you will add a external resistance to it. Okay. Now you can calculate this particular resistance through a receiver. Okay, and receiver, every element has its own resistance, so there will be a particular resistance to it. Okay, now you have a fixed I value that you can get from to this particular system. Okay, you can get a particular I value for a particular system. Okay, now you want to alter this I value with a process, set temperature. Okay, set temperature. Irrespective of the material or the manner of sensor or a transmitter you have, that will always have an internal resistance that will alter the current, and it will lower down to a certain value. Okay, it will lower down to a certain value. Now what you have to do is you want to provide a certain kind of voltage to it. Okay, so voltage can be higher. Opposite polarity of opposite polarity, so the net voltage reduces. Okay, and if you alter this voltage, the current is going to alter, and that alteration can be sensed by, or you can say received by this receiver, and you will get a particular value. Till now, is there any doubt? Let me just once again repeat it. Okay, well, let me just once again repeat it till now. You have a circuit. It will have infinite current. It will have infinite current. It will have infinite current if there is no resistance. You add an external resistance to it so that your current should be in limit. Then you can have a particular receiver which will have its own resistance, and you can calculate the current, or you can receive the current. Okay, now you want to alter this current with an outside behavior, and in order to alter that behavior, what you are going to do, you are going to introduce a system which is called transmitter. Now transmitter is an external agent that will have its own resistance. Okay, that will have its own resistance, but transmitter will primarily alter this current by changing the voltage that it is supplying to the current loop. By changing the voltage, and that voltage is of opposite polarity. Remember that this voltage is of opposite polarity, and you change this particular voltage. Okay, you have receiver. The receiver will receive the altering, or you can say changing current because of change of this particular voltage. Okay, till now are you aligned with it? Till now are you aligned with it? Class, kindly respond. Okay, okay. I think that it is the most simplest way that we can go. Okay, okay. Now your only job is to alter the current. Now your only job is to alter the voltage that has been supplied through transmitter. Now I told you about the transmitter, that there are two kind of transmitter that we have seen. One was your two type of, you can say, sensor, transducer, which consists of sensor and transmitter. Okay, but transducer mainly is about the sensor only, which is connected to transmitter, and transmitter transmits, or you can say an integration. Now you can see that, let us first take an example of our RTD, not RTD, let us take an example of our thermocouple. So thermocouple was something like this. Okay, and this thermocouple itself was giving an voltage. Okay, it was giving an voltage which was processed by transmitter. This voltage was entirely processed by transmitter, and this transmitter was working somewhat like an amplifier. Transmitter was working somewhat like amplifier, which was amplifying it. Okay, let me use AMP, amplifier, which was amplifying this and giving this voltage to your current loop. Okay, for a thermocouple, you got a voltage, you got an amplifier. That amplified value has been fed into the current loop, which was like something like this. It itself has its resistance, which will be always in series. We have added an resistance. We have a particular receiver, which has its own resistance added in series, and you have an I. Okay. So from a thermocouple, due to temperature difference, you get an current or voltage. That voltage has been supplied through transmitter, amplified and transmitted to, you can say, your current loop, closed current loop. Okay, are you aligned till now? Class, are you aligned till now? Okay. Okay. Good. Now let us move on to our resistance type. Now when you have a RTD, which is a resistance type, it will have its own resistance, because of which what will happen? The transmitter will have a voltage supply. A voltage supply will be given to the transmitter, which will be embedded with this kind of resistance that has been shown by this. This circuit will be completed with this resistance. Okay. And now we have an external voltage supply which has been applied to it. Okay. Now this voltage supply is giving us a voltage, which this constant voltage can be altered by this resistance. Okay, now this altered resistance will give us an altered voltage, which will be fed into the current loop, which will result in the let me use a resistance. Sorry for the handwriting, but I think the concept has been clear now. Okay, let me repeat this. Your RTD will have a varying resistance. A voltage has been applied across this resistance. The resistance will change because of the temperature. This will provide us an altered voltage. That altered voltage will be, you can say, amplified or processed through transmitter so that it can be compatible with this current loop. Through this current loop, your current will be altered with this altered applied voltage. And through this altered current, you are going to sense the change and you are going to calibrate it. Okay. So now you understood that in the starting of this session by Mr. Ryan, he said that the transmitter can be external voltage applied or not depending on the sensor. Now you understood the statement. Now are you aligned to this? Or should I repeat it once more? I think the picture is very much clear. If you have any doubt, kindly convey it to me. There is no issue. We all are very much supportive to each other. If someone is lacking behind, we all will come hand in hand and will proceed with the same line. Okay? There is no issue regarding that. Only Abhay, Hitesh, Bhanu, Aprajita, Adarsh have no doubt. Rest others, do they have any doubt? Kindly respond if you have any kind of doubt. If you want me to repeat, then I am happy to repeat also. And I completely understand that might not be getting to some few students. I completely understand. I was that kind of student who doesn't always understood it in the first time. Okay, very good. If you all understood it, if the thing is very much clear to you, I am the most happy person right now. Okay, 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 okay. Okay. Thank you, class. Thank you. Okay, okay, great. So now let us just complete what was left in this video part.
Needs to be. And there's current control circuitry in the transmitter that is used to regulate what current passes through the transmitter. And because current's the same everywhere in the circuit, that current that passes through the transmitter is the same current that's going through the rest of my loop. So the transmitter is what's responsible for controlling what current is allowed through it, rather than essentially having no control over the current, in which case you wouldn't have a means to transmit a process variable. You have to have something in there that actually regulates the current. Using that flow analogy, the transmitter would actually be a valve that you were opening or closing to regulate how much flow at any given time was going to be allowed through your pipe.
Okay. Great.
Hope that answers your question.
That valve one really makes it relevant. We've got time for one more question, and then we'll have to move on. And this is from Chris. Chris says, correct me if I'm wrong, but passive loop means you provide the 24-volt power supply, and active loop means 24-volt power supply is built in.
You are absolutely correct. The general terminology is that if I have a passive loop output, then I have all of that current control circuitry, but I don't have any voltage power supply built in. So I can regulate a current if you give it voltage, but that's it. An active output has some kind of integrated power supply into it. So you likely will have those same two pins. You'd have your plus and your minus for your output, but now there's a voltage supply built into the transmitter, and it's going to be driving the current out. So you don't need an external power supply.
Okay, good, great questions. Keep them coming. We have a few more slides to go over with Joe, and at the end we'll have another session with some questions. And so great. It's all yours, Joe.
Okay. So now hopefully we have a fairly good idea of what makes up that 4 to 20 loop and how it functions. Let's talk about why people choose to use it. The number one reason is that it's simple to wire and configure. Because you're just making one big loop with your wires, it's easy to connect those up. All of your devices will only have 2 pins on them, a plus and a minus. And if you do have a problem in your circuit or you want to trace how it works, all you're doing is just walking your wires around this loop, making sure that everything's connected properly. It tends to use less wires and connections than some other possibilities. If I were to compare it to something much more complicated, let's say I had a Modbus device, which is a serial communication protocol, and it's talking on 5-wire RS-485. Well, now these are more complicated terms I need to know. I've got these 5 terminals on all my devices. I have to wire this up as a big serial bus that gets very complicated and hard to follow if you have problems. 4 to 20 is much simpler when it actually comes to doing the wiring. Longer distances are okay without losing signal as opposed to voltage output signals. You'll recall that the wire isn't really relevant to a 4 to 20 milliamp loop in almost any case. It does have a voltage drop associated with it. So if instead of a 4 to 20 signal, I was using, say, a 0 to 10 or a 1 to 5, well, now I'm measuring voltage, and I may have some kind of a voltage transmitter that would regulate my voltage at the transmitter, but then I would have a voltage drop across the wire and other components. And now I have a problem because my receiver's not getting exactly what I'm outputting from my transmitter. You avoid that entirely by going with current, because current's the same everywhere in the loop. whereas I'd have wire voltage drops and junction voltage drops everywhere else. It's got a low sensitivity to electrical noise. That's very important for applications in, let's say, flow, where you have a millivolt signal coming out of a flow meter and you can't do much with it. You can't take a millivolt signal and run it very far because you have all sorts of noise problems. Similarly, a thermocouple is essentially measuring a millivolt signal. And again, you can't run it very far without running into all sorts of problems. 4 to 20 lets you avoid all that. You can run it long distances. You will pick up some noise, but because it's a powered signal, it's unlikely to affect it very much. And lastly here we have, it's easy to detect the loss of signal or power. That goes back to this idea that if I have 0 milliamps, I know there's a problem. If I have a 0 to 10 volt signal, well, is that 0 volts? Is that open circuit? The fact that
Class, my question to you is that they have mentioned it that low sensitivity to electrical noise. Okay, so current loop have one more advantage, that it is very less sensitive to your noise. Why is it so? Do you know the reason? My question is, do you know the reason? Yes or no? And if you know, write the reason. If you don't know, write no. Okay, okay, okay. So see, yeah. So see, do you know what is impedance? What is impedance of a particular circuit? Impedance. Total reactance, or you can say, yeah. Total hindrance to a flow. Okay, whether it is an electrical circuit or it is a mechanical circuit, whenever there is a hindrance, a particular hindrance to a flow, then it is called impedance. Okay, and why it is so much immune? Because see, it is always seen that it is a 4 to 20 milliamp, a very low amperage of signal, and this low amperages of signal will have a very low impedance in it. Okay, and because of that low impedance, it is very much immune to the external excitations. Okay, so this is the reason. If anyone asks you that why is it so that the current loops are immune to, first of all, knowing itself that it is immune to noise resistance, the first question that can arise is that why current loops are so much in use. So the answer to this is that it is what I can say, that the current is constant throughout the loop, so no error. Again, current has low impedance, therefore it has immunity to voltage. Another answer. The answer itself is very much sufficient for giving you a very different, you can say, vision, or your vision will be very different. But if they ask that why so, then you can say that because of impedance. Okay.
I wired it wrong, did some device lose power? You don't know. With 4 to 20, you always know if your wiring is correct, and you generally know if your devices are functioning or not. So with all those pros, why wouldn't you use a 4 to 20 signal? Well, the biggest reason is that you only get one parameter transmission. And what I mean by that is that you have a 4 to 20 range that can send out one variable. It could be transmitting a temperature. It could be transmitting a level or a flow rate. It could be transmitting a speed. But each 4 to 20 milliamp loop can only send information about one of those variables. If I have something along the lines of a multivariable level transmitter, where I have one transmitter that's capable of measuring the top level in my oil and water tank, the interface level between the oil and water, and the temperature of the material in the tank, well, I would need 3 separate 4 to 20 milliamp loops in order to send those 3 pieces of information via the standard 4 to 20 protocol. If I have 5 tanks and each tank has 3 variables, now I'm up to 15 loops I have to somehow manage. So as you get more and more complicated with the information you're trying to acquire, it might be time to start looking at other things, such as including HART, which is a serial protocol that runs on top of a 4 to 20 signal, or Modbus, which I mentioned earlier. Things start to get complicated, and all of a sudden you're finding yourself managing a large number of loops. And in those circumstances, there may be better alternatives. And the last 2 bullets here under con tie together, which is susceptibility to ground loops and the isolation requirements to avoid them. I could present an entire webinar on ground loops and isolation requirements, but for the purposes of the fundamentals, I'll sum it up by saying that when you have devices in your loop that accept or transmit multiple 4 to 20 milliamp signals. So for example, if I have a block of PLC DIN rail mounted units and I bring in 8 4 to 20 milliamp loops into those, I need to be very aware of whether or not they all share common pins, if their minus terminal for all those loops are tied together, and if a isolated power supply is required. Because if I'm not, I could get all sorts of strange ground loops where all of a sudden, instead of having isolated loops, which transmit their values nicely, I start sharing current between loops, and then you're going to get all sorts of problems. You're going to get signal averaging problems. You're going to get voltage supply problems. You open up the door to a whole bunch of different problems that are going to be hard for you to diagnose. So again, when you start getting a complex system that's using multiple 4 to 20 loops all going through one device somehow, you need to take a step back and be very careful what you're doing. But for simpler applications, the 4 to 20 loop is an industrial standard for a reason. And that's the first essential you need to know when it comes to takeaways from this webinar. It's an industrial standard for a reason. It's simple to use. And with a little bit of study, almost anyone can get it. So if you can use it, you probably should. Some considerations when choosing your devices, especially with 2-wire devices, you need to be aware of that loop drop. You need to know what that voltage drop is so you can make sure that your power supply supports it. You need to make sure that if you have a device that has multiple 4 to 20 milliamp loops going through it or from it, that you have the isolation requirements met. And you need to be aware of how many parameters you're going to try to be transmitting in your system as a whole so that you can plan accordingly for it, because you need one loop, one transmitter for each one of those parameters you're trying to send. And lastly, when can you not use 4 to 20 milliamps? Well, essentially anytime you don't have a transmitter in the system. If I have pulse outputs coming from a flow meter or a rotary encoder, or I have a thermocouple RTD, I have a pressure gauge that needs to directly measure pressure on the inside of a pipeline, then I don't have a transmitter to get me into the 4 to 20 milliamp world. And my choices are either find a piece of equipment that will connect up to whatever that sensor is, or find a transmitter that will connect up to those things, and then bring me into the 4 to 20 milliamp world. But once you start seeing that you're directly connecting up to a sensor and not a 4 to 20 transmitter, you have to start planning a little bit more to decide whether or not you need to get it in the 4 to 20 world or equipment that's available to work with what you have.
Yeah, let us just look at the summary also.
So to sum up, we talked about the definition of the 4 to 20 milliamp current loop, what the different components are that make it up. We discussed the pros and the cons. There's a lot more pros than cons, especially for simpler systems. And we talked about a few things for you to keep in mind when you start working with these loops. And Bruce, before we wrap up, you had a question?
Yeah, thanks everyone. As we're looking at this, we're going a bit longer than the.
I think for current loop, I think this is enough. So, guys, do you have? Are you aligned to this? My question is that now you know what is 4 to 20 milliamp current loop, why it is important, what are the pros and cons, why, what is the difference between the prime objective was to let you know that what is the difference between a digital kind of sensor and an analog kind of sensor, how they entirely different from its working and all. So, are you aligned to this class? Can you please answer this? Are you aligned to it? Have you understood uh, the concept? Not only the concept, are you aligned that the main reason so that we can change your aspect of learning, your you can say domain of knowledge. I think there is a very prominent shift in your knowledge domain at this point of time. The way you have looked towards the factory automation earlier, I think there is a difference now. Okay, okay. So just I will have a very quick one-on-one interaction with all of you about the actuators. Also, I will just give you a brief of sensors after that, just in order to understand it what kind of output that I have given to you. Okay, so let us start with Abhay. Kindly tell me that what kind of outlook has been changed by attending this session till now. Abhay?
Hello.
Yeah, Abhay, yes.
Sir, the outlook opinion changed towards the for factory automation is we are using different types of sensors such as analogs and digital for means we are dealing with some current we are dealing with current proofs and voltages.
हाँ बेटा हिंदी में भी बोल सकते हो कंफर्टेबली बोलो कोई इशू नहीं है गलत भी बोल रहे हो कोई दिक्कत नहीं है बस एक आपसे ओवरव्यू मांग रहा हूँ कोई क्वेश्चन आंसर नहीं हो रहा है किसी के साथ भी नहीं हो रहा है कोई भी जज करने वाला नहीं है हम सब एक है हम सब एक लेवल पे ठीक है ना
यस सर जैसे कि हम मतलब यूज करते हैं डिजिटल सेंसर्स और एनालॉग सेंसर्स तो एनालॉग्स के लिए हम बेसिकली करंट लूप ज्यादा प्रेफर करेंगे क्योंकि इसमें करंट जो थ्रू आउट द लूप होता है वो सेम होता है
मतलब आपको डिफरेंस समझ में आ रहा है कि एनालॉग डिजिटल कहाँ पे क्या यूज करना है क्या एप्लीकेशन हो सकती है थोड़ा विजन बढ़ा है उसके बारे में
यस सर
ओके थैंक यू ओके आदर्श
यस सर सर एक तो सर ये कि हम लोग एनालॉग और जो डिजिटल सेंसर्स है उनकी वायरिंग किस तरह से करते हैं कहाँ पे हम लोग सर्किट में किस तरह से यूज करते हैं ये सब समझ में आया सर
ठीक ठीक है ओके ओके प्रोसेस के बारे में भी आप थोड़ा डेप्थ में गए हो ओके ओके अपराजिता ओके भानु भानु
sir, basically now that how the process is working in industry, just like we came diagrams that how actually the process, how energy is flowing, that thing is working. So
okay thank you
I think that which we were earlier unable to cover.
Okay, thank you, Van. Hitendra? Hitendra Singh? Hitendra? Okay, Hitesh Sandhu? Okay. मुस्कान जिंदल.
यस सर. सर इसमें इमीडिएटली समझ आया कि मतलब 4 to 20 मिली एम्पेयर का मीनिंग क्या है रियल हम.
ओके ओके, थैंक यू थैंक यू थैंक यू. नयन. डिजिटल क्या है होता है, डिजिटल और एनालॉग में क्या अंतर है, क्यों कनेक्शन में डिफरेंस आता है ना. ठीक है. राज नंदिनी.
सर सेंसर्स के बारे में पता चला और एनर्जी फ्लो डायग्राम के बारे में पढ़े, और अभी जैसे ये 4 to 20 मिली एम्पेयर ट्रांसमीटर था इसके बारे में पढ़े, इसके प्रोज कॉन्स.
सचिन कुमार. थैंक यू राज नंदिनी.
Sir, we know more specific about system and the analog sensor और digital sensor कब यूज करना चाहिए ये पता चला है, और सर ट्रांसमीटर के बारे में और रिसीवर के बारे में काफी आइडिया लगा है.
ठीक. ओके, थैंक यू सचिन, थैंक यू. साहिल. साहिल गुप्ता. Different sensors and 4 developers. Okay, sir. Okay, sir. शुभम कुमार.
सर सेंसर के बारे में पता चला कैसे वर्क करता है और ट्रांसमीटर वगैरह.
ओके ओके. सुनिधि सिन्हा.
यस सर. सर एनर्जी फ्लो देन डिफरेंट सेंसर्स के बारे में अभी के क्लासेस में 4 to 20 मिली एम्पेयर के वर्किंग के बारे में, देन प्रोस कॉन्स सबके बारे में.
थैंक यू. वरुण कुमार.
हेलो.
हाँ वरुण बोलो.
हाँ सर, एनर्जी फ्लो डायग्राम कैसे बनाते हैं और सेंसर्स के बारे में, डिजिटल एनालॉग सेंसर्स उनका सर्किट डायग्राम यूज कैसे करते हैं, कनेक्शंस, और फिर ये 4 to 20 मिली एम्पियर इसके प्रोज कॉन्स, इम्पोर्टेंस क्या है.
Okay, thank you. So let me now just give you a brief about. I think we have 15 minutes more. So let me just give you a brief about sensors. उनके basic working principle देख लेते हैं हम कि कैसे होता है. ठीक है. Then we will leave. Conclude the session. बच्चे, मैंने जैसे ही बोला बच्चों से कि थोड़ा इंटरेक्ट कर लेते हैं, आधे कितने बच्चे भाग गए? 6. आई थिंक 5 बच्चे भाग गए. इंटरेक्शन से इतना क्यों डर रहे हो बेटा? आपको इंटरेक्शन हमेशा ही करने पड़ेंगे, और जितना अच्छी प्रैक्टिस कर लोगे उतना ही अच्छा आपके लिए. चलो, एनीवे, लेट अस नाउ मूव टू द सेंसर्स. So first of all, you know the definitions. I'm just giving you the stimulus and sensing. So for acoustic, the stimulus is acoustic. Then you can calculate the amplitude, phase, spectrum, velocity, and wave. If it is biological and chemical, you can look at the fluid concentrations. If it is electric, then it can be charge, voltage, current, electric field, conductivity. For magnetic, it will be magnetic field, flux, permeability. For thermal, temperature, flux, specific heat, thermal conductivity. For mechanical, there can be position, velocity, acceleration, force, strain, stress, pressure, torque. Again, about choosing, there can be environmental factor, economic factor, sensor characteristics. So sensitivity, range, stability, repeatability, linearity. So error, response time, frequency response. Then environmental factor can be temperature range, humidity effect, corrosion, size, overrange protection, susceptibility to EM interferences, ruggedness, power consumption, self-test capacity. This we have covered in that video, the RTD, thermocouple, thermistors, semiconductors. Okay, these all have these basic, either they are exponentially varying or linearly varying according to this particular formula. Displacement, position, and proximity sensor, we know, we have learned about it through videos. Okay, a potentiometer, you can see that there is a slider, there is a particular load, and the voltage output can be varied according to the displacement. Okay, so this, you can say this joint can move to and fro with this a rotary potentiometer, and there can be a linear potentiometer also, and basic working principle is similar. Then you have strain gauge. So your delta R by R is proportional to your epsilon, which is your strain. Okay, so the resistance of this material will change because of a particular strain. So you can, through strain, you can calculate the force, you can calculate the metallic properties, you can calculate various things through this principle also. Then you have capacitive. Now you can see that if the plate move in this particular direction, the capacitance is going to change. In this particular direction, this will change. If a dielectric moves, then also your capacitance change. Now if the relative positions are changing, then also it changes. Then you have tethers with stretch like springs. Now you can see in this particular, if there is a movement or acceleration, this will change. Okay, these are fixed and this is moving. Overall capacitance is changing because of acceleration. So it can be a very good accelerometer. Then you have LVDT. Yeah, you can see that it is linear variable differential transform. So what here happens is that there is a primary which will excite. There is secondary. Okay, secondary 1 and secondary 2. Now when this will move, okay, so there will be change in this particular output and this particular output, and then change will be capitalized by your LVDT. Okay, and RVDT also, you can say that it has a cardioid shape, or you can say a shape of a heart, and that cardioid shape has a reason why it is of a cardioid shape, because cardioid shape is only kind of shape that can give you variation in every degree. So when there is this particular degree, there will be variation, this degree there will be a variation. That is the reason that we use cardioid shaped piece of magnetic material. Then you have eddy current proximity sensors, you have secondary coil, you have reference coil. Eddy currents are produced because of this relative magnetic field into a metallic material, and those eddy current will hinder the magnetic field of this sensor coil, and with the change of from the reference coil to this sensor coil, there will be a current passing through it that will trigger, and at some preset level this change can trigger a switch. Then again you have inductive sensor, you have your amplitude drop, then you have Schmidt trigger, then you have amplifier. Okay, now this is a signal processing loop, or you can say characteristics, that all these are required for signal processing. Okay, again the reluctance is shifted because of the induced eddy currents into this, and this reference current changes, and we can get an output. Then pneumatic sensor, you can see that air is passing through this. Okay, and when a material, whether it is a metallic or non-metallic, when it comes near to this, okay, there will be a rise in pressure, and these escaping air will continue to provide a particular pressure, and that pressure, rise in pressure, can be detected because of the presence of a particular material. Then you have optical encoders. You have this encoder, we will take into details into servo motors also. So you have this particular LED and light sensor with a particular disk. You can see that these track can be sensed by a particular sensor, and we can get some datum position about, and we can increment the encoders also, and we can have absolute encoders also. Then this is a proximity switch, this is manual switch, this is rotary switch, and this is tappet. Okay, again same kind of function. This reed switch we have covered in a video. Hall effect sensor, we all know that when a beam of charged particle passes through a magnetic material, okay, through a magnetic field, the force act on the particles and you get a negative charge will be attracted here. There will be positive charge and you will get a current passing through it. This is Hall effect sensor. Again, tacho generator, you have a pickup coil, you have these teeth, and this teeth will have varying reluctance, and because of varying reluctance, you will have a pickup output, and through output, you can calculate the speed. Then you have pyroelectric sensors. Pyroelectric means because of heat. So you just need to learn the material or memorize the material that it is lithium tantalate. So question might be asked that what kind of pyroelectric sensors are used. So it is lithium tantalate. Again, it senses the temperature, or you can say not temperature, it senses the heat flow. Again, the temperature is different, heat flow is different. You can say heat flow is the flux of heat that is traveling. Similar to kind of current, the current is analogous to heat flow, and your temperature is analogous to voltage. Okay. Then piezoelectric sensors, we all know that because of vibration of force, if charges come into a particular material, it is called a piezoelectric material, and vice versa. If there is a material that produces current because of force, or if it vibrates because of the passage of current, then that is a piezoelectric sensor. Now this is a tactile sensor. It has polyvinyl fluoride film here. Okay. So now you can see that this is a soft film and this is a AC input. So this film is also piezoelectric in nature. So what happens is that when this input is provided, okay, so current is not passed through this field, but vibrations are passed. So since this film is vibrated, you will get a particular output. But when there is a tactile force applied to it, when there is a touch applied to it, then what will happen? The alter and output voltage will be occurring, and this output alteration is calculated or sensed. So all your touch screen, all your touch pads are based on this principle only as far as tactile sensors are concerned. Then you have photoelectric sensors, and then you have ultrasonic sensors. Okay, so it is an electronic device that measures the distance of target objected by emitting ultrasonic sound waves and convert and reflect sound into electric signals. A very brief introduction about the working principles only. Okay, so I think I have covered it into the time. So is there any doubt, class? Okay, Hitendra, there is some network issue. No issues. No issues. I think there was some network issues for other students also. They texted me regarding this. So did you get it? Okay, so I have just given you a very quick brief. If you want me to elaborate it more, I can take a separate session for this. This is a class for dedicated for a single session, but I have tried to cover it in 5 to 10 minutes because I thought that I think that you might be knowing about it. You might be learning about it at lot of places. So should I continue with this for a longer session or is it enough? Class, kindly respond. Just a brief about it I have covered. If you want me to cover it more, I will cover it. I have no issues in that. Class, kindly respond to that question. Is it enough? Okay. Okay, class. Thank you. So I conclude the class for today. Okay, I think it's 16:56. We have 4 more minutes. So I conclude the class for today. We'll meet tomorrow. Have a nice day.